Good afternoon, and welcome back to this series of webinars dedicated to masonry buildings. Today, we are focusing on the problem of global and local analysis of existing masonry buildings according to the European Code, Eurocode 8, Part 3, in its current version. Last time, we have seen this slide, which is summarizing how Eurocode 8 Part 3 is approaching the problem of the assessment of existing masonry buildings. We have seen we have a first phase dedicated to getting knowledge of the building, a second phase dedicated to the analysis, and the third phase, which is dedicated to the retrofit. Today, we are focusing on the analysis problem, which is divided into phases: the local mechanism analysis and the analysis of the global in-plane mechanism. As I was mentioning in the previous webinar, I will refer to Eurocode 8 Part 3 in its current version, but I will integrate it with information taken from more, let's say, newer code, specifically the Italian Building Code of 2018, because the Eurocode 8 Part 3 is currently under review, and probably the new version of the Eurocode 8 will have some parts, some new concepts that will be probably similar to the ones that are now in the new Italian code. So let's start from the analysis and verification of global mechanism. The topic that I will cover today are the modeling criteria and global analysis methods, the in-plane mechanism and strength criteria. Then I will introduce the concept of equivalent frame modeling of walls. I will then present the constitutive laws of the reinforced masonry elements, and I will give a brief description of how to model diaphragms, and then I will move to the core of this first part of the webinar, which is the nonlinear static analysis or pushover analysis. Starting from the modeling criteria, we can say that masonry walls are the vertical subsystem of the lateral resisting system. They transfer horizontal forces to foundations, and they are usually made of piers, which are elements with a vertical axis, and spandrels, which are elements with an horizontal axis. Diaphragms are the horizontal subsystems of the lateral resisting system, and they are connected walls, and they can be made of floors, roofs, or walls. A portion of masonry able of coupling the response of vertical elements, which are the so-called spandrels, can be considered part of the resisting system, provided that two conditions are valid. First, they are supported by a lintel or an arch, which is assuring the support even when spandrels are damaged or cracked. The second condition is the fact that these spandrels are sufficiently anchored in the adjacent walls. For example, horizontal tensile strength is present, or when a diagonal strut resisting mechanism is able to develop. And that's, for example, can take place when there is a tension resisting element which is coupled with a spandrel. Now, when performing global in-plane analysis, a fundamental assumption is the fact that local mechanisms are prevented by the presence of proper elements, if necessary, of course. Based on the relative strength of the elements of a single wall, different mechanisms can take place. For example, if you have spandrels that are weaker or weaker than piers, you will have a so-called spandrel mechanism. You will have spandrels which are damaged, and so the mechanism is controlled by piers. On the opposite side, if you have strong spandrels, damage will be concentrated into piers, and so you will have a soft story mechanism. Of course, reality is somehow in between, because in reality, normally mixed mechanisms are taking place with damage both in piers and spandrels. The distribution of horizontal actions among the walls depends on diaphragm in plane stiffness and also on the efficiency of wall-to-diaphragm connections. In case of complex buildings and in case of bad wall-to-diaphragm connection, this distribution of actions is complicated and is subjected to uncertainties. However, as regards diaphragm in plane stiffness, three situations are generally possible. The first case is the one corresponding to infinitely rigid diaphragms. Now, in this case, horizontal actions are distributed among the walls based on the strength, on the stiffness, and on the position of the walls. If the diaphragms have a finite stiffness, these diaphragms are able of restraining walls, and also in this case, they are able to distribute seismic actions. On the opposite side, if the diaphragms are characterized by negligible stiffness, they are not adequate to distribute horizontal actions among the walls. Now, moving to the global analysis methods, Eurocode 8 is firstly giving some general, doing some general considerations, which are reported in section 4.4.1 and section C.3.1, which is specific for masonry buildings. The most important general consideration regards the crack stiffness. So you are required, or at least it is suggested, to use in the model crack stiffness, both for flexural and shear stiffness. In absence of accurate evaluation, you are required to use a crack stiffness equal to 1/2 of the corresponding uncracked stiffness. Then Eurocode 8 is listing the possible analysis methods, subdividing between linear analysis methods and nonlinear ones. Among the linear analysis methods, we have the lateral force analysis, the Q-factor approach, and the modal response spectrum analysis. Now, these methods can be applied under various conditions. The most important are the fact that the lateral load resisting walls are present in both the horizontal direction of the building. The walls have to be continuous along the height. The floors have good connection, at least a significant in-plane stiffness, and good connection among the walls and among the walls and the diaphragms. You are required also to have a difference of the in-plane stiffness among the different walls, which is somehow not exceeding a limit value. Spandrel elements included in the model are made of blocks which have a good interlocking with the adjacent walls. Linear analysis methods consist, which are the lateral force analysis and the Q-factor approach, are somehow similar, and they consist in applying a distribution of forces calculated starting from the demand spectrum, with or without the Q-factor. Then you are required to calculate the actions on the elements and perform a check in terms of moments or forces. In the Q-factor approach, you have to reduce the design elastic spectrum by a value of Q given by the code. Regarding the modal response spectrum analysis, you are required to calculate the response corresponding to the most important modes of vibration, starting from the elastic demand spectrum and then combining the effects. Moving to the nonlinear analysis methods, we can discuss firstly the nonlinear dynamic analysis. This consists in calculating the response of the building, directly integrating the equation of motions of the building subjected to a set of ground motions. Of course, you are required to use models that are somehow able to model, to capture the cyclic behavior of masonry elements, also in the post-elastic phase. And they should also be able to capture the energy dissipation. If the response is obtained using at least 7 ground motions, you are allowed to use the average of the response to perform the safety check. Otherwise, you have to use the maximum, so the most unfavorable value of the response. Then moving to the nonlinear static analysis, we can say that this is the preferred method for the assessment of existing buildings. And I will discuss it in details later on. As regards the in-plane mechanism and the associated strength criteria, Eurocode 8 is specifying which are the capacity models to be used in the assessment in this section. For both piers and spandrels, two mechanisms can control the strength: the flexural mechanism and the shear mechanism. The mechanism with the lowest strength is controlling the element's behavior. However, the strength associated with each element is depending on the level of axial load acting on it, and so through the so-called interaction domains. So varying the axial load can potentially vary the strength. Now here you can see a summary of the possible mechanisms of a pier. You can see here, for example, the flexural mechanism, which is characterized by rocking of the pier and crashing at the two. And here you can see some example of shear mechanism, which can be characterized by sliding at the base or by diagonal cracks, which can be inside the bricks or inside the joints. Regarding the flexural mechanism, Eurocode 8 is saying that the corresponding strength is given by this expression as a function of d, which is the length of the element, the axial load n, h0, which is the distance between the section where the flexural capacity is attained and the contraflexure point, and as a function of this parameter, which is the normalized axial load, which depends also on the mean compressive strength, Fd, of masonry, which is reduced accounting for the confidence factor. Regarding the shear, Eurocode 8 is considering also the shear sliding mechanism. The strength is given by this expression, which is a function of this shear strength FVD multiplied times the area of the compressed section. Not the total area, but only the area of the compressed portion of the section, because d prime is the length of the compressed part only. FVD is given by this expression as a function of the initial shear strength and of the friction coefficient, and has this upper limit, which is depending of Fm. Now, Fm is called in Eurocode 8 compressive strength, but it has not to be interpreted as the compressive strength of which was used in the compressive strength of masonry, which was used in the flexural behavior, but is more the compressive strength of the brick, because if you look at literature work discussing this criterion, here you can see that this is the compressive strength of the bricks. As I was saying, strength is depending on the axial load through this interaction domain. Here you can see that, for example, for a pier characterized by a low axial load, you will have a flexural mechanism, which is controlling the response. But if you increase the axial load, you will have probably a shear mechanism controlling the response. And then, if you go towards very high axial load, you will have again a flexural mechanism. Of course, in a nonlinear analysis, the axial load can vary. Regarding the spandrels, you can have again two mechanisms, a flexural mechanism and a shear mechanism, this time with cracks, with diagonal cracks only. Now, if you look at literature regarding this topic, you can find specific strength criteria developed for spandrels. However, I'm not discussing here because Eurocode 8 is not, in the current version, is not prescribing specific criteria for spandrels, but is using the same criteria that I was discussing before. Now, the concept of equivalent frame modeling. Equivalent frame is a very common modeling strategy for masonry buildings. It consists of identifying spandrels and piers on each wall. Usually, you are firstly identifying spandrels, which are the portion of masonry between vertically aligned opening. Then you move to identify piers. You now have the problem of selecting the proper height of the pier. There are several criteria that are doing that. And finally, the remaining portions of the walls are the rigid nodes. And then you will have this equivalent frame schematization of the wall. That's the modeling strategy that, for example, is used by the software Tremuri. Now here you can see an example of equivalent frame idealization with reference to a real building. So you can see the wall and its schematization with piers, spandrel, and rigid nodes. As I was saying, equivalent frame model can account for the variation of axial load, which can take place during nonlinear analysis and actually also during the real behavior of the building under an earthquake. For example, if we consider this simple wall and we are focusing on this element, this pier, this is the interaction domain of the piers. Now let's assume of having an horizontal action which is rightwards. So this pier probably will have an increment of axial load, and it will be characterized probably by a shear failure, or at least a shear mechanism. If the action is reversed, probably this element will have a reduction of axial load, with the possibility of being, say, its behavior being dictated by a flexural mechanism. The following topic are the constitutive laws for the elements that you are required for a nonlinear analysis. Eurocode 8 is suggesting the use of elastoplastic models with limited ductility. So the force versus drift law is a law of this is represented by this plot, where this is the strength and the drift limits is given by the code, depending on the mechanism. For example, and also depending on the limit state, because for the significant damage limit state and for the flexural mechanism, the drift limit is given by this expression, so 0.8% times the ratio between H0 and D. For the shear, a fixed value of 0.4% is prescribed. In case of near collapse limit state, these limits have to be incremented by a factor of 4/3. Now, at this point, I should discuss the problem of modeling diaphragms. I'm not doing the here simply because it will be probably a topic of one of the next webinars. Just I want to say that they are normally, or at least in the software Tremuri, but the equivalent frame discretization, they can be modeled as elastic membrane with equivalent parameters. Now, moving to the nonlinear static analysis, Nonlinear static analysis has two steps: calculation of the capacity, so determination of the pushover curve, and calculation of the demand. Here I will discuss only the first topic because this one will be the topic of the next webinar. So what's pushover analysis? Pushover analysis consists in applying gravity loads and a system of distributed horizontal forces at the story levels, which are proportional to the inertial forces and have a resultant force equal to the base shear FB. Force are scaled to increase the horizontal displacement of a control node DC, which is located at the highest level usually. The curve FB versus DC is the so-called capacity curve. At least two distribution of lateral forces should be applied. A uniform pattern, which means that the forces are proportional to the masses, uniform because the acceleration is uniform along the height, and a modal pattern where the forces are proportional to the lateral force distribution determined in an elastic analysis. Lateral loads should be applied at the location of the masses at the story levels. Here you can see, say graphically, what I was discussing before. You can see the concept of distribution of forces to be applied, the concept of control node, the displacement of the control node, the base shear, and here you can see the capacity, an example of the capacity curve. Now, if the diaphragms have negligible stiffness, you have to perform the analysis of single walls. Otherwise, you can perform the analysis of the wall building, and DC is the mean displacement of the walls weighted based on the masses. Once you have the pushover curve, what you are required to do to perform the assessment is to identify the capacity. Capacity is identified in terms of global displacement DC. For example, Eurocode 8 is defining three different limit states. Regarding the near collapse limit state, it is suggesting that the ultimate displacement capacity is the displacement corresponding to a decay of the 20% of the base shear with respect to the peak shear. Regarding the significant damage limit state SD, the displacement is calculated as 3/4 of the displacement corresponding to near collapse. Finally, regarding the damage limitation limit state, the capacity is the yield point of the bilinear curve of the equivalent single degree of freedom system. Now, all these concepts that I was discussing are somehow embedded in the Tremori software, which is able to perform a pushover analysis of a wall building being consistent with Eurocode 8 Part 3. Here, for example, you can see a very simple model that has been subjected to pushover analysis. Here you can see the resulting pushover curve, and here you can see also one of the walls with the indication of the possible mechanisms that are taking place in the elements, also with the extent of damage. And then here you can see the calculation of essentially the capacity and also the demand corresponding to this building. Then we can move to the analysis and verifications of local mechanisms. Regarding this topic, I will discuss firstly which are the possible local overturning mechanisms. I will then introduce the local analysis methods, and particularly I will refer to the nonlinear kinematic analysis, which will also require the definition of an equivalent nonlinear single degree of freedom system oscillator. To perform the assessment, we will have to discuss also how the seismic input is defined, because it is defined in terms of the so-called floor spectra. And finally, we will arrive to discuss the verification in terms of acceleration. Now, this topic of the local analysis is not discussed in Eurocode 8 Part 3, at least in the current version, so we refer to the Italian code NTC 2018. Probably it will be discussed in the next version of Eurocode 8. So local overturning mechanisms are partial collapses due to loss of equilibrium of portions of masonry. They can be influenced by different factors, such as the geometry and the restraints, the presence of vertical loads, the amount and distributions of vertical loads, the connections among the structural elements, such as tie rods or friction forces, the quality and strength of masonry, and the efficiency of connections among the walls. Different local mechanisms can take place in a building. Here you can see some example. Here, for example, you can see the simplest, which is called simple overturning. Here you can see the overturning of this portion of masonry, and this mechanism can take place when no restraint at the top is present, and also the connection with the orthogonal walls is not very good. Here you can see a more complex mechanism, which involves also a portion of the orthogonal wall. That can take place when, again, the restraint on top is not very good, but the connection with at least with these orthogonal walls is quite good. Regarding the vertical bending, that's a mechanism that can take place when the restraint on top is quite good, but the connection with orthogonal walls is not very efficient, and also the connection with the diaphragms at this level is not very good. Finally, the horizontal bending can take place when the connection at the top, the restraint at the top is not good, but the connection with the orthogonal walls is good. Now, the code is allowing for limit analysis, which is called kinematic analysis. That consists in considering a rigid block mechanism where the rigid blocks are defined by crack planes. And it consists in calculating the load multiplier alpha, which is the ratio of the horizontal seismic forces, and the weight of the masses of the kinematic chain. In the commentary to the Italian code, two approaches are presented. One, which is the linear approach, consisting in calculating the horizontal action load multiplier alpha 0, corresponding to the activation of the mechanism. This leads to a verification in terms of acceleration. Then there is also the nonlinear approach, which consists in calculating the variation of the load multiplier during the evolution of the mechanism, which is represented by the displacement of a control node of the mechanism. In this case, verification has to be performed in terms of displacement. Now, in this webinar, we'll focus only on the nonlinear approach, on the linear approach, sorry. How we can perform the assessment? First of all, we have to identify all the possible mechanisms. And for each mechanism, we then have to transform the real mechanism into a single degree of freedom kinematic chain based on the identification of rigid blocks. For each mechanism, we then have to calculate the load multiplier alpha 0 corresponding to the activation of the mechanism. We then have to minimize alpha 0 in order to identify the real mechanism. In case of the nonlinear analysis, we have also to evaluate the relationship between the load multiplier alpha and the control node displacement. To calculate the activation load multiplier, we have to apply to the blocks the following forces: the self-weight of the blocks, the weights carried by the blocks, and then a system of additional forces which are external forces, internal forces, for example, the one coming from tie rods, and a system of horizontal forces proportional to the weight which are not carried by blocks, but whose mass is generating seismic forces on them. Given a virtual rotation to each block, it is possible to calculate the displacement of the point of application of all the different forces, and then alpha 0 is obtained using the virtual work principle, or also consideration based on equilibrium at least for simple mechanisms. So alpha 0 is given by these expressions, where, for example, at the top you will have the vertical forces, and at the bottom you will have the horizontal forces that are multiplied by the activation multiplier, the load multiplier corresponding to the activation of the mechanism. Alpha 0 is an upper bound estimate of the multiplier, so you will have to minimize alpha 0 to get the real load multiplier. Then you will have to define the single degree of freedom oscillator equivalent to the mechanism. Now this is done with all these expressions that are particularly useful for the nonlinear analysis. For the linear analysis, the only parameter which is playing a role in the verification is this one, the ratio of participating mass, E star. Once you have defined the load multiplier, you then have somehow to determine the demand. The demand is related to the seismic input and is represented by the so-called flow spectra. That's because the building acts as a filter between the soil and the mechanism, modifying the seismic input of the mechanism. So you will have to represent the input using the flow spectra, which are depending on several parameters: the periods and the damping of the modes of the global structure, the modal shapes and the participation factors of the global structures, the height of the base of the local mechanism to be considered, and the period and damping of the local mechanism. Now, in the code, there are various methods to define the flow spectrum. I won't discuss them. I will just present this one, which is the one called simplified formulation. In this case, the spectrum is given by this expression, considering for simplicity only the fundamental mode of the building. Here you can see that this expression is a function of this quantity, which is the contribution of the fundamental node to the maximum floor acceleration. Now, the last part of the assessment is the performance of the verification in terms of acceleration. In the linear analysis, you are required only the load multiplier corresponding to the activation of the mechanism. You can carry out the verification at both the damage limit state, if required, and the verification corresponding to the ultimate limit state, SLV. However, the capacity at the damage limit state is used also for the verification at the ultimate limit state, so I will present also that one. How to perform the verification at damage limit state? First of all, you have to consider a value of damping equal to 5% for the oscillator equivalent to the mechanism. Then you have to calculate the capacity starting from the load multiplier. First of all, you have to apply this simple formula, starting from the load multiplier and the parameter E star and the confidence factor. Once you have applied this formula, you will have to distinguish between two situations. A situation where the mechanism is initially rigid. Now, in this case, the capacity, or better, this expression is representing the capacity in terms of acceleration. If the mechanism on the other side is initially elastic, so the mechanism is free to vibrate, this expression is representing the capacity in terms of spectral ordinates corresponding to the period of the element T0. So once you have identified the capacity, you will have to move to the capacity in terms of ground acceleration. So you will have to move somehow from the floor spectra back to the spectrum at the ground. So you will have to identify the capacity AG SLD corresponding to the attainment of the capacity in terms of floor acceleration or floor spectral ordinates. And then you will have to check that the capacity is greater or lower than the demand associated with the limit state. The demand is represented by this quantity AG corresponding to the probability of exceedance of the seismic action. Once you have performed the verification at the damage limit state, the verification at the ultimate limit state is somehow straightforward, because the capacity at the ultimate limit state is simply the capacity at the damage limit state multiplied by the behavior factor for the out of plane verification, which is assumed equal to a value of 2. Again, once you have the capacity, you then have to compare the capacity with the demand, against in terms of acceleration corresponding to the probability of exceedance associated with the ultimate limit state. Also, in the case of the verification of the out-of-plane mechanism, the software Tremuri is able to perform this verification in terms of the linear kinematic analysis. Here you can see again a very simple building. Let's imagine that we want to check the out-of-plane behavior of this wall, which is that one in a plan view. Now here you can see the facade that we want to check. What you can do is to draw the mechanism that you want to check. Here, for example, I wanted to check the overturning of all the facade, but what you can do is to draw the perimeter of the mechanism to be checked. I wanted also to check only a simple overturning, so I was adding only an hinge at the base. And here you can see the mechanism that I want to verify. Now in that case, the software is performing the calculation of the capacity and also of the demand, both at the mechanism, both at the two limit state that I was discussing before, an ultimate limit state, but also a damage limit state. Of course, if you want to verify more complex mechanism, like the one I was discussing at the beginning of this part of the webinar dedicated to the linear analysis of local mechanism, you can do. It's simply left to the user. Now with this, I have concluded what I wanted to say in this webinar. So I would like to thank you for your attention.